All right, we're about to get started. This is the HPC Python course offered by TAC, and this is Antonio Gomez.
Can you hear us online? And well, people here, yeah. Hey, that's fine. So just checking that at least people in the chat can hear what you're saying. It's okay. We'll wait a little bit. Okay, so we wait a minute and a half if that's okay with you guys. Yeah, okay. So we have all these. Let's try to do that. So welcome to the Python for HPC or HPC Python tutorial. It's been a while since the last time we had a Python tutorial. So let's see how it goes. Well, just to let you know, guys, it's not this tutorial is not about Python syntax. So if you don't know the syntax, well, sorry about it. Also, it's not about. We are going to be talking about MPI. It's not an MPI course. So MPI questions, we'll try to answer them, but it's not about that. But anyway, let's see how it goes. So first introduction. I always think every time we talk about Python that we have to justify why we use Python, why users use Python on HPC. Traditionally, they just say, oh, HPC, you use C, C++, Fortran, you're done. Well, why do we use Python? First, it's easy, kind of. The code is really nice. At least I really like it. They always say that it's great for prototyping. I don't agree with that. It's not only great for prototyping, it's great for anything you have to do. When people say it's just for prototypes, it means, to me, it feels like you cannot do real code with Python. That's not the case at all. Also, a great thing that Python has is that it has many third-party libraries. Pretty much, there are many things that you want to do. Well, before you start doing them, go and check it. Someone, okay. We don't have in Stampede in our system, we don't have all the libraries, all the Python libraries in the world. It's impossible, but you can install libraries in your own account, and that's something that we are also going to show today. Okay. So the main characteristic of Python is a dynamic language, but it's also a strongly typed language. What does that mean? Well, all the objects in Python, they have a type, and this type is determined at runtime. The variables in Python, they are just a value bound to a name, where the value is going to have a type, but the variable itself doesn't have a type. You can see Python objects like boxes. And inside of this box, you will have your value. That value will have a value type assigned associated with it, but the big box doesn't have any type. It's just a Python object. And everything is an object in Python. The interpreter is going to keep track. And one important thing here is you can do anything that is incompatible with the type of data that you're working with. Remember, everything is a Python object, but if you try to do a string plus string, it's going to work because you will concatenate the strings. If you try to do integer plus integer, it will work, as expected. But if you can try to do a string plus integer, the interpreter is going to say, I don't know what to do with these things. They are not compatible. They are both Python objects, but inside the big box, there is a tiny box saying that they are. In Python, there are mainly two data structures. One is the Python list, which you can call them arrays, because actually they are dynamic arrays. They allow random access, and it's an index structure. All the items in this list are Python objects. That means that you can have different types of variables in the same list. It's not just you are going to have a list of integers. No, you can have integers, strings. They also, since it's a random access structure, you can insert and delete at any random position. And the other data structure is dictionary. Dictionary is just an associative array composed by key and value pairs. It's indexed by key. This key can be a string or a number, and this key is going to be unique. And the value can be any Python object. That also means that in any dictionary, you can have values of different types. Doesn't matter. The question always is to store a value associated with a key and extract that value from the dictionary. This is like in C, C++, any map. Okay. So Python and HPC, well, one thing that you will hear is that always that Python is very slow. Is that true? Yes. Can you fix it? Kind of. So if it's slow, why should you use it? Well, first thing is that, because you already have your code, you're not going to rewrite everything in C or Fortran. And that is a very valid reason. Second point is that because you like Python, you really know a lot of Python, and you're starting your new code, why not using Python? So if you already have your code, or if you're developing your own code and you want to use it in HPC, what should you do to actually do an efficient usage of the HPC infrastructures? And that's what we are going to try to answer today. And Stampede, which is going to be the machine that we are going to be using today, we had 2 Python modules. One is a little bit outdated, the Python 2.7.3. Please don't use that one. Most of the problems that we have with Python and Stampede is because people use that old module. And we also have Python 2.7.6. Please use that one. That's a good one. Okay. Also, very important, as I was saying before, there are many libraries. We have many libraries already installed in Stampede, but there are many more. If you need an additional library, you can install it in your own account. These are the commands that you can use in your own account, and it will install that module in your own home.local or any other folder that you decide. Once you have done it, you can use that module. And you didn't need any help from anybody. You are in control of your own module, your library. You can do with it whatever you want. Also, it's a good idea. We're not going to talk about this today much, but it's also a good idea to use virtual environments to create different Python environments with different libraries that you can use. So here, most of the people, you guys have laptops. So if you can check and if you have internet connection, we are going to connect to Stampede. Please, all you have to do is just, if you are from XC, use those 2 commands at the top. If you want to use your TAC account, you can use this SSH-y. Replace your username by your TAC username. Okay. Let us know if you can connect to. Are the slides available now? Oh. Yep.
So what's the reason why you do -y instead of -x?
You can do -x. We were trying yesterday. There is a reason for it. There's a special credentials being transferred when you do -y extra. And if today, considering the conditions that we are going, well, the environment that we are going to use, if you use -x, works perfect too. Okay. But sometimes, if you see that the x are not being correctly forward, try with -y and see if that works. This is, yeah, extra credentials. Yeah. We had that case.
But it turns out it doesn't matter.
Yeah, it doesn't matter. But sometimes if you find a problem, try with -y. So are you all on Stampede now? Yeah. Okay, so we are going to copy the examples. Just you have to run these commands here that we have. So copy from the user string 00, Python, HPC. You can copy to where you are right now. Then extract this. Okay, and this will create an examples directory where you will have the different examples that we are going to be running inside. Okay. Are we all there? We're working trying to put your slides online, so you will be able to copy paste within just a few minutes. It's going to be much better for everybody. Okay, have you been able to copy the file and extract the file? So the next thing is just we need to load the Python module, the 2.7.6 we were talking about. For that, we also need the Intel 14 module. So we do module load Intel/14.0.116. Right? And then you do module load Python 2.7.6. Okay? So this is the environment that we need. If for some reason today, during the tutorial, you have to exit the terminal, please at least do these two modules again. Okay? You have to always have these two modules. Have you all loaded the modules? These two modules? Yeah? Okay, so we continue. The other thing that we will need to do is to submit a job to the queue to work in a remote nodes. Ideally, in Stampede, you cannot run stuff in the login node. Why? Because the login nodes are all the users are right now we are connected to the login node of Stampede, login 4 in my case. You might be in login 1, login 2, login 3, I don't know. Users shouldn't be running stuff there. That's it. So you always have to submit a job. So we are going to submit an interactive job with -t in this case. You have to ask for this allocation. Yeah, sorry. Good catch. Yes. There we go. Yeah.
Be able to say yes.
Yeah, say yes, please. And something that you want to do is to open a second terminal, if I can. So you want to have a second terminal usually, and we are going to need a second terminal in the login node. Okay. So if you can do the same thing, SSH in a second terminal, and leave it there. Okay. We are going to need, for some reasons, for some specific reasons, we are going to be, although I said that you're not supposed to run anything on the login node, we are going to be running small examples in the login node, okay? And this has something to do with this Y stuff. Anyway, that's why you're going to need 2 terminals. Anyway, so we continue. We're not going to be talking much about profiling today, but in Python you have profiler. Why do you need to profile? Well, you have your application. You want to find where your code is actually slow. It's that simple, because you want to focus on that part. That's what you want to fix. And so the way to invoke this profiler is just you call Python -m C profile and this name of your Python script. Okay, so I have it here. So we go to examples. We go to one intro. Yeah, and every time you see code in this presentation, and the title in the box will tell you the path where you can actually find the code. Okay, so you don't have to type all that Python code. It would be useless. So here we have this example, profiling example. We are not doing anything useful. We are just showing a message, hello world to everybody, and then we just iterate through over a list. Then we create another list and operate on the elements of that list, some square root, sorting, a lambda function. So all we want to do is just Python. Yes, check that everything is correct. -m C profile. Profile. And it will give you something similar to what I have in the slide. All this saying is that you can check with your code, and this is a very trivial example. It's saying that most of the time is being spent in line 12, which is the vector function, together with, it's a weird thing because it says it's spending most of the time on line 1, as you can see here. Almost all the time is being spent there. And why is that? Because first line is just from math import square root. What's happening is that most of the time is being spent in the square root function that is being called here in line 17. Sorry, line 15. Okay, you can see here I'm calling square root all the time. So there is well, we will see today how there are things you can do about it. So instead of calling the Python square root, you will call the C square root, and that will improve your performance. So this profile is what you use to get ideas of what you can do with this, with your code. Okay.
Can I ask a question?
Yep.
So there's several two time columns, maybe, I mean, or there's a total time column.
Yep.
And then a work column, cumulative. So which column are you looking at? When you say most of the time,
the cumulative,
spent
cumulative, this one.
cumulative time.
Yes.
And what's the difference between columns? What's total time?
That's always a good question. I never look at that.
Okay.
It's like when you time your code, there are 3 values that it returns. You always look at one, and the other one is like whatever.
And so you say that most of the time is being spent
Here in this square root.
And it's because that
It's because you have this list of almost 1 million elements, 700,000 elements.
right, but why is that? Why is it modular? I mean, why isn't it saying vector? Why isn't it saying you're spending all of your time in vector, in the function vector? That's where you're spending all your time, right, in vector?
Yeah.
But it doesn't say that. Oh, what's the difference between the first line which says 0.514 in module, and
Yeah.
the second line which says 0.499.
The first one also includes the time that you spend loading the module, loading the function.
Line, so
Yeah.
that should be fast. It should be
Yeah,
fast.
but it adds a little bit of delay in this.
You mean so the thing that takes the most time is actually loading the module?
No. So you will see that there is a difference between the call to vector and the call to the to SQRT, and it doesn't make any sense if you think about it.
Say it again.
If you see it here, the call to the vector function takes shorter than the actual call to the SQRT function, right?
Well, so there's another line that says math.sqrt, so I'm still a little confused about
No, but-
why line 1 is the square root.
Yeah, and that is just the actual call to the function, just the call, the jump, the unconditional jump.
Oh, so it's just the call but not the work.
Yeah. And we are calling that.
And so how, I mean, I've never looked at one of these before, and so how would I know what that line 1 where it says module, how would I know what that means? I mean, module means, that there's some, you've got some Python code in a
Yeah.
file.
Yeah,
It's called a module. So what does it mean?
that all the time is being spent inside that module,
What module?
math module. Okay.
So, and if you were importing from more than one module, would it tell you the difference?
It depends on the number of calls that you're doing to the functions in that
I
module.
mean, what would it say? Would it give, like here it just says module?
Yeah, I would say the line here.
Oh, the line number.
Yeah. It's not the best profiler ever. I have to agree with you in that. Okay, so that's kind of the introduction to this course. The main goal was to get you set in the environment that we're going to be using. And now we're going to look at the Python. Are the slides available? Huh? So if you guys want, all the slides are available in the web. So it's a good idea for you to go copy the slides, or at least to have a look at them, because you're going to be copying code and you don't have to type everything. It's going to be better for you.
Where are they? They're on the training page associated with the slides.
Okay. So once you know how slow your code is, you're going to try to speed it up. This is, we go again to the theory, to the boxes theory in Python. This is a Python object, and this is just, when you do a equals 8, this is what happens in Python. You have a Python object which is a, which has inside an integer and 8, and this 8 has the type int. Okay, but you have around this box, and you have more stuff. I'm just simplifying this. So again, I would say this many times today: Python is nice, the development is really fast compared to the languages, but it's slow. And the bottlenecks that you find, that you know that you have in your code, you can rewrite them. You can use any of these technologies. Many people talk about NumPy nowadays. We don't support NumPy in Python, in Stampede, but we are going to be focusing today on Python, okay? At least in this part of the presentation. What's Python? Well, Python is just Python with C types. Instead of having the big box, in C you just have your integer, which is a 32 bits, 64 bits, whatever. That's what you want to have. Basically, any Python code is a valid Python code. There are a few exceptions, but you don't have to worry about that. What you do is you translate your code into C or C++ code, you compile it, and you use it as a module from your Python, from the Python script. You can also call C libraries, which is, instead of using the square root from Python, we can call the square root from C, which is much faster. One important thing here is all the code using Python and Python. You can intermix them. You can call Python from Python, Python from Python, it gets really confusing. Don't worry about it. And one important thing about Python is that what you're going to be doing is just tell Python what data types you have. Instead of saying, I have this Python object, you're going to say, this Python object is an integer, or a float, or double, whatever. The more information you can provide, the better the performance, okay? And that's where it gets really interesting and difficult this way. So this is, for example, if you have all this, if you guys have the slides, you can just copy paste. So we are going to be trying IPython for this example, or just type IPython. And the first 2 lines are just IPython specific. Don't worry if you don't use IPython. All we are doing is just because you're going to see later how to use Python. You have to compile and you have to invoke it from external files. Using IPython, we are going to avoid the hassle for this, for example. So that's what these 2 first lines are doing. It's just they are creating this kind of magic environment, Python magic environment for you, so you don't have to worry about compiling. It's going to do everything for you. So we are going to load extension Python magic. And now, sorry, I put one, it's only 1%. There we go. Now, twice Python, we import math. And this is just a very random function that I just made up for this tutorial, okay? Python. You will see here something that you don't have in Python. I already declared that the argument to this function is going to be an integer. That's not normal Python. If you try to do that in Python, Python is going to say invalid whatever. You need a comma, or because this, I don't know what int is. Int is a variable for Python. Okay. So then we say we copy this. Okay. We enter again. Oh, this is when it gets confusing. Sorry. I was doing this in the login in the remote node. We don't have compiler in the remote node. I forgot to mention this. Can you? I told you before to have a login node session. Okay, so in the login node, sorry about that, and that's probably going to happen more today. Wait, I had to do the same thing.
That to me on the
yeah. There you go. There you go. So I'll do the same thing. No. Just putting an extra. Where's this thing copying so much? Anyway. Okay. And now I call this. And this part here, this is not Python. This is just Python calling Python. So what we did here was to compile this function, this first Python, because we are passing an integer, and it's running this in a compiled version of that. Okay, and you're going to see more examples of this, especially in the next slide. If I can go to the next slide. There we go. So if you have the slides within IPython, please try to type all these or copy paste all these. What's going to happen here? We have our first Python function. All the functions are identical, but they have different things. So the first one is a pure Python. No integers, no nothing. And we're going to see how long does it take to run it? Okay. Then we are going to load Python, and we are going to run a first version of the same function without even decorating the code. Which is what's going to happen is that Python is going to take this and compile it. Okay, and we're going to compare how fast that is compared to the non-compiled version. And then the last sample is going to be passing an integer, so decorating your code a little bit. Okay, so if you can try this sample again, the login node. You're not supposed to run there.
You were saying that it has been compiled. I didn't see you give compiled command. Can I see that? Can I see that something has been compiled?
We are going to do. I don't know if you can see it here. It should. IPython keeps that.
But so now that it has been compiled, you can also work the other way.
What do you mean the other way?
Well,
Here, if we find it, yeah. But we are going to do. This is part of IPython. Now we are going to do the thing where you actually are going to invoke ICC and create your own library. They use IPython for tutorial purposes, and I still don't like it because it hides stuff, you know. Okay, sorry. Good. No. 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 Did you do it? I broke your thing.
No, it's not. Where do you want this one?
The terminal.
And the other one.
You can hide that one.
Where's your other one?
Yeah.
Where's your other stuff?
Yeah, hide.
That one.
Hide.
Is this your
No, hide.
non-PF?
Hide. And hide that one. So it's the only
Where's
one.
your-
The only one you didn't open. Here. So we're going to do this sample. So import math, the first Python. Click on this. It's putting white spaces everywhere. Swim. We call time it function. And it's a very small example, but so it's running in 400 nanoseconds. So very fast, right? But let's see what happens when we do the Python part. What happened?
You left out the S.
So
Yeah,
I call it like this.
yeah.
No. You know, I'll do it again. But I know working Python now. Sorry. Have you been able to run it? Right? No? Okay, no? Okay. So before it was running 450, now it's down to 350. And this is just exactly the same code that has been compiled, okay? Exactly, no difference whatsoever.
Where's the 1 million loops?
Sorry?
1 million loops, where's that the first?
And that is the timed function deciding how many loops it's going to run in order to create the statistics.
Oh.
It's not just one execution.
So it actually ran it a million times?
Yeah.
Took an average?
Yeah.
Yes.
Yeah, that's the only reason why we are using IPython, just for this timed function. Decorate this code with just the integer as an argument, okay? You saw that it went down to 350. Now we're going to try decorating our code. We do Python again, import math, def fast Python, and this is the only difference, integer as an argument. Everything else, I just even copy and paste the same the calculation, so you don't say that I'm lying or anything like that. I'm just going to remove that in case it complains. Okay, so now time it. So it's just by putting that extra argument, it went down to less than half of the original execution time. Okay, and we can do much more, and that's what we are going to do in the next exercises. The effort required for this was just running on the login now, but it's small. Okay, so if we move to the next slide, it allows me to go there. So it's not just about declaring your variables like integers or doubles or floats. You can also specify Python functions. In Python, you always define your functions with cdef. We know that they always take Python objects as parameters and they return Python objects. You can declare C functions. C functions are declared with cdef. Okay, they take either Python objects or C values, and then you go there and decorate your arguments. There is another one that I didn't put here, which is called cpdef, but forget about that. It introduces an overhead. If you can avoid it, avoid it. These functions, they can call each other within the Python module, but from the outside, if you are calling this Python module from a Python code, you can only call Python functions within the module. And we are going to see an example, meaning in your module, you will have to have a Python function calling the Python functions, okay? Unless you use cpdef, but we are not into that. So I was saying, you can decorate your variables. You can say that a variable is a double, that an array is an integer, or array of integers. This is how you declare functions. This function is going to take a double as an argument, and it's going to return a double, and it's a C function. Your whole class can be a Python class. Just declare this class. This is the normal Python class declaration. You just put cdef. You can create structs, and you can put more than one declaration in the same cdef declaration. Okay, so why do you want to do things like declare objects like C of C type? Well, it's giving you advantages like when you are calling if you're from within the object, if you're calling the object methods of the same object, it's improving the performance there because it's all C code. It doesn't have to interpret anything like in Python. So your function calls are going to be much faster. In our examples today, we are just going to be calling the function once, so it doesn't make much difference. If you had several functions calling each other, it wouldn't make much difference. But when you're actually calling the functions many, many times, it's like inlining functions in C, okay? It makes a difference. So this is the first test that we are going to run. This is just a Python code, normal Python, nothing Python there. And we are just going to call it like we go to 2_Python. And all we have to do is we are just going to call this time Python test Python and see how long it takes. Again, this is just a function that I just created. Imagine that this is the core of your calculation, okay? So we are just focusing on that function. It took 15 seconds to run that function, okay? You can also run it in your account, no problem. If I have editor somewhere, applications, I just want to do, well, can you remember 15 seconds? Yeah, so I don't worry about it then. Okay, so our original code, Python code, took 15 seconds. And that's what we are going to try to optimize. Now, in the login node, again, please, otherwise it's not going to work. You have in this folder, in samples 2_Python, you have this myfunc1.pyx. That's the Python extension. What we're going to do is to create a library to compile the first compile the function, which is the same function that we were running before, just a little bit decorated with some doubles. We're going to compile it, or first create the C code, then we're going to compile the C code, generate that dynamic library, and import that library from Python. And run exactly the same code from Python calling this function, which is now compiled, okay? So what we have to do is we first call Python myfunc1pyx, okay? And this has created a myfunc1.c file, which is the C equivalent to your Python code. We can have a look at it. It's not going to be nice. You can try to understand what's going on here, and you can even try to write it by hand. Good luck. But your function is there somewhere, okay? This function here. I can promise you that. So now we're going to compile this C code, right? So we just ICC -shell -f PIC -o3 myfunc1.c -o. So that's going to be our library, dynamic library, yeah. And now we just put the Python path. Yeah. Did it work? What we have now is an SO file. This is our dynamic library, which is implementing the code that we already had, that we had before inside. Yeah. We all have the SO file. If you have any problem, just let us know, and I mean, we can stop, and no problem at all. Okay. So all we're going to do now is call this SO file from our Python code. The Python code is this one. It's test Python1.py. All it's doing is importing this library that we just created, the myfunc1.so, by doing import. And we are just calling the function that is inside of that module, which is the function that we define in the Python file, right? Is that okay? So all we have to do is just call time Python test Python1. You already have that file there. Yeah, and before it was 15 seconds. Let's see how long it takes now. 9 seconds. Okay, it seems that we have done a lot, because it's kind of messy that you have to compile, you have to call Python, then you have to compile, then you have to import it. Don't worry, once you try 3-4 times, you understand the whole workflow, and it's not that difficult. So by doing little, because we haven't done much, we already 60% of the original time. Okay? Did it work for you guys? Yeah? But so before we go to the next one, in this first Python test, all we were doing was just telling that the argument was a double and that the result was a double, right? We can see it here, this argument, and the result that we are returning is a double. If you think about it, if you look at the code, you say, well, what else can I do? Yeah, I could put that this function is a C function. But I'm just calling this function once. It's not going to give me much difference. From 9, I'm not going to be able to go much lower than 9 seconds. There is one variable there that we are not defining the type, and it's the key to that. Anybody can figure it out? That's correct. I here is the main issue that we have right now. We are not saying what I is. So I right now in this for loop is a Python object. So we are iterating over a Python object, meaning that we had to check the type of I every time, and then we have to use it. And that's slow. So the next example, all we are doing is just, well, I'm decorating the function, but don't worry about it. I'm saying that the I is an integer now.
Wouldn't it make a big difference to do a C function instead? Because you have a loop and Python loops really slow.
What?
So, well, you're saying it doesn't make much of a difference. It's just make the function itself.
Here, because here all the difference is just for when you're actually invoking the function. And we are just calling it once in this case. So it's just, if you're calling the same function many times in Python, you want to do even the whole declaration of the function like C. Okay.
Also helps make like range. Yes.
No, it's just the call. It's just it creates less entries in the table for function table. Yep. So if we try this code now, we call Python func2 pyx. Again, it creates my func.choose.c. Right? Now we call again ICC.
So if you run Python from the computation modes, but not, it doesn't have the ICC.
In the development queue, you do have ICC, but we're not using the development queue. That's the issue. Let's see. There we go. And now remember the first sample, the pure Python was 15 seconds, first Python 9 seconds. Now let's see this one. We are down to 5 seconds. So again, by decorating I and the arguments, we are down to 33% of the original time. So you're improving quite a lot. If you're calling this function all the time, you really want to do this kind of compilation. Yeah.
Do you actually need to keep around the PYX file? Like, if you wanted to, you could not.
I mean, the PYX is your actual code. If you don't care about your code, you can delete it.
Like, could you still import it?
No,
Just VSO.
you're just using VSO. Okay, but don't delete your code. Okay, and you look at this code, it's like, well, there isn't much else to do in here. But I was telling you before that you can call C functions, and you can call square root C function instead of calling the Python function that we are calling right here. And that's going to make a big difference. And this is the code for doing that. You can import. So what we're doing is we are just importing the C square root function. There are 2 ways for doing that. The first line from libc.math C import sqrt, or you just like in C or C++ with the extern. So cdef extern from math.h double sqrt. You can choose any of those 2 ways for doing this. And the rest of the code is identical. well, we are not importing math anymore. There's Python math. Okay, but everything else is start exactly the same. So we are going to see how long it takes to run this thing. We compile the Python code. Now, there we go. Now we have this new library. And we are just going to call it from our test Python 3 is going to be calling this new function. Time Python test Python 3 p1. So it went from 15 seconds to 9 seconds to 5 seconds to 200 milliseconds. Okay, so these are things you can do to speed up your code. As you can see, it's an iterative process, Python. At some point, you just have to say, "I'm going to stop." Okay, and that's up to you, and that's up to how much free time you have. Okay, so, but it can get really. It's not difficult. It's just it's an iterative process. You try something, it worked or it didn't work. You try something else. So, for example, even figuring out that you have to declare the type for the variable that is iterating through the loop. Well, it might look trivial or it might not look trivial. Okay. So again, it's easy, kind of. People in Python, they will say that everything is easy. At some point, it gets difficult. It has a lot of potential. If we went from 15 seconds to 200 milliseconds, it has some potential. When I saw, for this trivial example, I saw the result, was like, I'm going to change all my Python code. I think it was like, no, that's not going to happen. So I also included here for you guys a link to a tutorial. You can try to follow. They also cover here strings and C++ objects. Something that we weren't doing here is that you can, instead of creating C code, you can create C++ code. So you are free. You can take this tutorial, try to play with it, try to do it. And we are doing this thing again. That should be fun. Okay, we are 1 hour into the tutorial, so I think we can take a break. You can play a few more minutes with these examples if you want to. And then we'll go and play with NumPy and Matplotlib, and I will try to answer questions if there are questions online. Or if you guys have questions, just let me know. Good.
So if you actually said you can define your own C function to call it. So there are several but yeah, there are lots. This is one no,
So I was using the type of text.
Okay. Everything good, yeah. These all want to we'll wait a couple of minutes and go to the next presentation. Okay. Just waiting for a couple of people, I guess. Oh, I don't have the X in this. It's going to suck. I don't have the X11 installed in here, I think. You need X11, right?
Yes.
You need that installed.
No way to X over the
Okay, we are going to run into some problems on my side, not on your side for this tutorial, this part. Anyway, so you're not going to be able to see we are going to be plotting and stuff, and this is not my machine, so we are not forwarding X here, so I'm not going to be able to show you the plots. But if everything is correct in your machines, you should be able to see some plots and some stuff. Okay. Anyway, okay. So this next presentation is about NumPy, Matplotlib, and SciPy. So we already saw how to, once you have your Python code, how to compile it to C. That can be nice. That can also be a hassle. It depends on you. And these are other strategies, especially in NumPy, things you can do. Where's NumPy? We have seen before, it's just Python. We have high-level number objects. We have integers, floating point, whatever. And it's just a Python box. We also have containers with lists and dictionaries. Well, Python is just an extension package for Python, yeah. NumPy, extension package for Python, from multidimensional arrays. So instead of creating your own list, your lists are going to be very slow. You create your NumPy array. NumPy arrays are closer to hardware, so the efficiency of this increases. They're implemented in C, so it's like calling C. I specifically designed for scientific computation. So we can see here, this is an example you don't have to run. Well, if you want to run it just in IPython, you can run this thing. We are doing the same thing here.
Could you make the text a little bit bigger?
Yep. You created a problem. There we go. So what we're doing in the first line, we're just importing NumPy. And every time you use NumPy, this is the de facto way to use it, import NumPy as NP. The second line, we're just creating a normal Python list of 100,000 elements. And we're just calling this function, which is just take each element of the list and square that. And that function with Python list is taking 6.43 milliseconds. Perfect. When instead of creating the Python list, you create a NumPy array with the same size. So we are going to do exactly the same thing. We do exactly the same operation by using the NumPy syntax. We went down to that nothing time. And it's exactly the same thing.
What's the time?
And
Oh, microseconds, is that what that is?
microseconds, yeah.
What?
Microseconds. Or nanoseconds, I don't know, because I had to do something for LaTeX or this. Nanoseconds, if I'm not.
Yeah.
Okay. And it's exactly the same thing. Exactly the same result. So yeah, if you have arrays, you want to use NumPy. It's that simple. Every time you have an array or a list in Python, forget about it, rewrite your code, use NumPy. And that's what you have to remember all the time. Done. There is no alternative. Forget about Python lists crap. Unless you have different type of Python of items in the list, you want to use this kind of array, okay? So why is Python so slow? Again, so each object has a lot of metadata around saying what our variables are, saying what you can do with them, what you cannot do with them, dimensions, other attributes. It has potentially really inefficient memory access, and we are going to see that now. It's also interpreted instead of compiled. So what you do is just you create your NumPy array, which is it's a single type. I mean, you're going to have integers in your array, or you're going to have doubles in your array. You're not going to be playing with different types. And it's going to be continuous storage. If you know C, Fortran, this is what arrays are in for. In C, you have continuous memory. Also, NumPy implements some functionality around these objects so that you can do things with these arrays. You can create easily, I always see people just creating 1D array, 2D arrays, but you can create n-dimensional arrays in NumPy. It also provides broadcasting functions. What is broadcasting? I'm going to do this a little bit bigger. If you want to multiply an array, this array of 1, 2, 3 by 2, you could do that, right? Or you can also do the NumPy way of doing this. It's just you just multiply an array by a double. I would broadcast this double into this other array to multiply the two arrays. That's what it says. It also has some tools for integrating C, C++, and Fortran code, and NumPy, yeah, it started like something kind of small, and it's growing and growing and growing, and there are many things around NumPy growing and growing and growing. So you can spend your life trying to understand all this. It has some very useful linear algebra capabilities. It has some Fourier transform, mathematical functions, random number capabilities. It's really good. So you want to really use those functions.
Can I ask a question?
Yeah.
About that broadcast, so you're saying the example on the right is equivalent to
Yep.
the example on the left. It's just easier to write.
Yeah, that's correct. It's the same thing. So NumPy is doing this transformation without you having to do anything. It's what they call broadcast. So these are all links that you can follow or to the documentation of the different functions that you have in NumPy. I just put them there for your reference. Again, we are not going to go through all the functions. You don't need them. I don't know all the functions. No one knows all the functions. It's just in your specific area, you're going to know more than I know about the functions that you actually need. So far, an NumPy array. Well, first is the data layout. So all the information is in is homogeneous and contiguous memory. So it's like C. So together they're in memory. That improves cache, improves everything. And it also has the so-called universal functions, or the U functions, which these are like functions that operate on arrays. They have been compiled. They're written in C, and they are vectorized. So they use the capabilities of your processor the best they can. They are going to be better than your functions if you want to write those functions. Okay. So this is the data layout. So on the left, you see an NumPy array. You have your Python box. You will always have a Python box. This Python box is saying, this is the head, and this is the data. And in the data, I just have all the elements of the array, one after the other, in memory. It has some extra information that you can use when working with NumPy objects. And this is a Python list. So when we were creating before a Python list, what it's actually doing is creating a contiguous array of pointers. So the first element of the list can be, I don't know where in memory. The second doesn't have to be next or even close to the first one. What happens when you are bringing that information from main memory to cache is cache miss all the time. And that's what makes this so much faster. Okay? And they look the same once because you can access the individual elements of the array the same way in a Python list, a NumPy array. So don't use a Python list. Okay. So these universal functions, they just operate on these ND arrays, and they're vectorized. So we don't have Python on the mic. I don't know, but with current processors with vectorization capabilities, you really want to use these functions. And this is an example here. I'm going to maximize. So this is a function. This is just we are importing NumPy and importing math, the numerical library of Python that we were using before in the Python examples. In the first sample, we just create an array of 100,000 elements, and we just call the syn function over each individual element of the array. Okay. First iteration, it takes 18 milliseconds. We are calling the syn function in the math module, in the math Python module. The next time, we just call the actually universal function of NumPy. So we just call NumPy.syn, which is the same function, and we apply that over the same array. It went from 18 milliseconds to 1 millisecond. It's a large improvement just because we are just calling vectorization, and then it's going to depend also on the processor that you have, how it has been compiled. Things that are out of your control, but whatever. You are getting an improvement by just calling a different function. And it's a function that if you didn't have a NumPy array, you couldn't be calling. Okay? And the other two are just examples of the same thing.
So you don't have to give the loop.
No.
For NumPy, you don't have to give the loop.
That's correct. So NumPy internally is doing the loop, and it's vectorized loop. So this is also similar to the broadcast that we were showing before. So NumPy does a lot of stuff for you. You can like it, you can like that, or you cannot like it. But even if you don't like it, just call this function if you can. Okay. There are many different ways to create an array, and here I want you guys to go and try. So you just create a Python session, write Python, whatever you prefer. And just do this. So we are going to import, I don't have, sorry. There we go. There we go, Python. So we import NumPy, NP. In the first example, NP array, what we're doing here is to actually pass a Python list that we created. We are creating it at the same time, but we are just passing a Python list, and we are converting that Python list into a NumPy array. Okay. Let's see here. Okay. Now A is a NumPy array. You could also create an array where each element is initialized by the index or the position of that, its position in the list. That is the function aRange. The function aRange also allows to give you a step. So we can say starting at index whatever, finishing at index whatever, with step. Okay. You can do the same or something similar for doubles. In this case, in space. So it's going from 0 to 1, it's creating an array of 5 elements, including both extremes 0 and 1. You can also say that you don't want to include the right endpoint. So instead of being 0, 0, 25, it has to be 0, 2, 0, 4, 0, 6, 0, 8. Then we have a set of useful matrix constructions. So you need to, it's a funny syntax that you have to use 2 parentheses here. And you can read more online about why you need that. It's just because actually this parentheses 4, 4 parentheses is just the first argument to that function. Meaning the MP1 function takes more parameters, and that's the syntax for declaring your matrix. If you forget about it, it's not going to work. Yeah?
What do you specify without integers or
you can specify the type that you are using. You can specify that you're using integers, booleans, strings. You can specify. We're going to see it. You can specify everything you're using. Huh? Ah, well, yeah. Well, this one. I always like this one, actually. Also, you can create. This will give you an empty or a 0 matrix with zeros. You can create a diagonal matrix. Again, it's up to you depending on what you need. And so here, if you have needs of this kind of matrix, you're going to find your function there. We also have the random capabilities here in NumPy. Yeah, so you can even initialize from random stuff, from random seeds or random values with Gaussians. Empty, all it does is just it creates a matrix and initialize, meaning it allocates a memory. Whatever is in memory, it's going to be the initial values for each individual element of the matrix. It's not going to be 0, it's not going to be 1, it's going to be uninitialized, okay? But you are just allocating memory. And again, also something here is that you can resize your arrays. Here we are declaring an array of size 10, initialized with 10 zeros, and now we are resizing that to be size 20.
To get what?
To be, instead of having 10 elements in the array, you have 20.
And will they be 20 zeros?
I don't remember if this is initialized or not initialized. I guess it's not initialized. It shouldn't be initialized because you're not in
I
it.
just tested it with zeros.
But I guess it depends on. It's like every time if I had to do this, I'm really careful about resizing. Then I'm going to check what you have. I'm going to force you to have what I want you to have. You know, it's just how you do it. Yeah, we'll catch you. So data types, C was asking before. These are the data types that you can use in your NumPy arrays. You can have booleans. You can have strings, integers of different sizes, unsigned integers, floats, and complex. Okay. I don't know if I'm missing something. No. Okay. So when you create your object, you can declare, specify which type you want. And here's for you guys to try some examples. Do you have the slides? Well, I'm going to try also here with you. So let's see. So we can do the following. Import NumPy as NP. If I create a NumPy object without specifying anything, so I'm creating a NumPy object from a list, from a Python list. Yep. NumPy is figuring out that what you have there are integers, because they look like integers. Okay. The same way that if you do one dot, now it's saying, well, I'm guessing that what you have there are floats. Okay. So NumPy is guessing what you have. Now, can you force NumPy to use the type that you wanted to use? Yes, you can. And all you have to do is here on the right side, it's going to be like the first example that we use with 1, 2, and 3 integers. But now we're going to tell it, hey, you use float. I'm initializing this with integers, but they're going to be floats at some point. You have to allocate enough memory for all these to be floats. I call it A, right? B type. Okay, I don't know how to type anymore. So now we create the array the same way we just told NumPy, hey, these are integers, but you're going to have floats at some point. So allocate enough memory for it to be floats. We are going to create now an array of booleans. Saying booleans, and with this, you can play with it. Meaning, you can take an integer list as well, and say d type equals bool. And now your d that you created with 0, 1, and -1 is actually false, true, true. Only 0 is the only false, all the other ones are going to be true. So you can force this thing, even saying, I'm giving you this, but don't worry about what I'm giving to you. Create this kind of data type. It would be interesting to start playing with strings and all that. So that is up to you if you want to play with it. That's something that you probably are going to use in real life. But yeah, so this is also how you create complex types. As I said, you can also have an NumPy array of strings. And it's a funny thing, when you create this array with the words bonjour, hello, and hola, the type that is returning is strings of size 7. And that is because it's taking the largest string there, which is when you're saying, oh, it has 7 characters, so you're just storing strings of size 7.
So it puts, does it give that much space to every?
That's correct. If you try to put more, you can run into trouble, but you can also initialize that with a larger type,
Yes,
more characters. As I said before, there are also linear algebra functions in this in NumPy. Okay, we can try to see what's happening here. This is just the dot product of 2 arrays. Let's see first what happens when I do a range of 3. It's giving me an array of 0, 1, and 2. So when I call this np dot, the arrange of 3, is multiplying 2 vectors, like vector multiplication. Okay, the dot product of 2 vectors. Here I also showing you how to multiply a vector file, the dot product of a vector and an array, and I'm doing this in this fashion here. It's a little bit funny how you do it, or this way of doing things. You create an array of 9 elements, 0 to 8, and then you're saying, what you had before, which is an array, I want to reshape it. I want to convert this array into a matrix of 3 by 3. And then I want to multiply that matrix by this vector of 0, 1, 2, and the result of this multiplication is going to be this array, right? So just basic algebra. It's not that I know much more about that. We have Victor here who knows a lot. But no, but again, so that if you have to use this functionality, you know what you have to use, but this is one of those functions to show the linear algebra capabilities of NumPy. And now we're going to do something quite fun, which is we are going to be able to use the mics. Do you all know about the mics that we have in Stampede? Well, when you go to our introductions to our tutorials, you always have to use the mic from C or Fortran code. We're going to use the mic from Python without changing anything at all in your code. No offload. That's pretty cool. Why? Well, this is called automatic offload. It's a feature of Intel Math Kernel Library, MKL. So when you're using MKL, you can automatically send your part of the execution to the mic. Okay? NumPy uses MKL for its linear algebra operations without you having to do anything. For example, you can call the gem functions, Cholesky. The mic is only going to start working when you actually have a decent size in your matrices. If you have a really small matrix, the time that you will spend sending the matrix to the mic, doing the computation, tiny computation, sending it back, it will be higher than actually running that on the host. Okay. There is here. This is a link with all the functions that support automatic offload. There ain't that many, so but you can go and check if you actually using those functions.
So not all of clause 3, for example.
No, I don't know specifically the details, but no, I think so. And I don't know if we know all the details about it.
I don't know all the specific functions that are,
Because it also depends on the compiler and all that, so it depends on the release.
but I'm sure that you don't have documentation.
Yeah,
Specific subject, so,
that's correct. When working with this automatic offload, there are these 3 environment variables that you have to use. One is nkl mic enable. Now, all we're saying with this is that we are going to use the mic. If you have a mic, use it. Second one is the number of threads on the host, because since we are calling nkl, we can use threads in the host. And the last one is the number of threads that we're going to have on the mic. Okay? There are other variables. We are going to be using one more, maybe, or it's up to you if you want to use it. But let's go and try. So, shit. It freezed. Okay. Okay, so you will have to go to the remote node. We're not going to be running this on the login node. Please don't do it. You will be kicked out the login node for this sample. Okay, so make sure that in your prompt you have something that says that you are actually the login node, or that you're not in the login node, sorry. So when you do a hostname -a, it's going to return a string like this. Okay? Are we all in the compute node? Yeah? Okay. So now we go to examples. Free offload. Here we only have one Python code. And we can have a look at this Python code. All what this Python code is doing is just creating two matrices of 8,000 by 8,000. And then it's going to run 3 times just to get some statistics. It's initializing those matrices with random numbers because we don't really care, just for training purposes. And it's multiplying those matrices. And this is what called the dgen call in NKL. We're going to do this 3 times just to get some statistics. Okay? So first, then we are just going to call my dgen.py. We don't do anything else. And let's see how long it takes. I have the module? Yeah, I think so. So now we just wait for the 3 executions to finish. So this is running in the compute node. We haven't specified to use mic. We haven't specified to use threads. So what is actually happening is that it's just running one thread of the compute node. Okay? And this is what you would expect usually with Python. It's going to take a while. But not so long. So if you have questions now, please, you have a couple of minutes to ask questions. Okay, so for in the second run, it's only 3 runs, don't worry, it's not that bad.
Let's see, in NumPy, we're using something called a range.
Yep.
Is it the same as, does it work similar to the range function in Python? Like, you're setting up an array.
No, the a range is creating the array. The range function in Python, you use it to iterate through that range. So it's giving you the independent.
It's a range, it's a sequence of numbers.
Yeah.
And a range must be doing the same thing, except creating it in
Yeah,
NumPy
and creating the NumPy object.
array.
Yeah. Okay, so it's almost done. You should create a smaller matrix. Yeah. Okay. No questions. Are you guys running this, or is just I give up? It's the Intel Xeon Phi coprocessor that we have in cores. Yeah. You have 60 cores or 61 cores, and you can use up to 4 threads per core. while on the host, which is what you are running right now, you have 16 cores. Okay, so okay, it finished. It took 45 seconds to finish. So, and now we're going to do, as I said, this ran in only one thread of this compute node. Now we're going to do export OMP threads equals 16, because we have 16 cores in this machine. We're going to run exactly the same thing. So we are not changing the code. We are not doing anything. Okay.
So you just set up the automatic offload.
Not yet. Right now, we are not even using the mic. We are just using all the cores in the host. So even if you don't have a mic, you can still use the threads that you have in your machine. So if you go to a different machine, that is not a Stampede where you don't have mics. So it went from 45 seconds to 5 seconds. And again, you didn't change your code at all. No one saw me doing anything, right? So, and now we are going to use the mic. I'm going to do export nkl mic enable equals 1. Export mic OMP underscore OMP non-threads equals 240. Now we are going to run the same thing. So I never touched the code and didn't do anything at all.
To make this work automatically like this, did you have to untie with NGL library?
Yeah, that's correct. With the in Stampede you don't have to do it, but if you're compiling your own NumPy, you will have to ask us. You can send a ticket and ask us, but yes, you have to compile. So it went from 45 seconds the first time, just running one thread, to 5 seconds in the second, running 16 threads, to now an average, just keeping the first one. The first one is always a little slower, to 1 second. Without changing the code, just using threads and using the mic, we went from 45 seconds to 1 second. It's a pretty decent timing, performance optimization. You didn't have to change your code at all. Just using, you were just using what we provide here, tag. Okay? I hope no one ran in the login. So that's NumPy. There are much more about NumPy, but again, you have to go into specific functions on NumPy. It depends on the user, and it's kind of pointless to go through something like that here. Now we're going to talk about matplotlib. Matplotlib is just the library for plotting 2D and 3D. It produces publication quality figures. That is important. So this is not so much about HPC. Now it's about showing the results that you have, which is pretty much, it's more important than actually running stuff on HPC. No one cares about your job if you don't publish. That's kind of how it works. It provides an interactive, there's a typo, an interactive environment. You can create plots with histograms, bar charts, error charts, scatter plots. Again, this is pretty big. I don't know everything about Matplotlib. Every time I had to go and plot something very specific, I go to their website and try to see how to do it, because it's impossible to remember all the different possibilities, to be honest with you. And this is a very simple example that it will produce that plot. If you have the X configured, it will, when you run this sample, it will show a window with this plot. In my case, it's not going to work because this is not my laptop. It's not configured for that. But I can show you, if you're doing the right thing, if you just type Python and this file, a window will show up with this specific example, with this specific plot. And all we're doing here is just, we're just plotting this series, this 1, 2, 3, 4, 5, 6, with blue dots. So you can see it here. And we are also plotting a second series, 6, 5, 4, 3, 2, 1. We're not specifying anything else. I'm just going to plot green line. And we are just saying that we are using the X label and A label, just some random text, and it will produce this result. Okay?
So it doesn't show anything until you get the show through.
The show will fail. But
Does it create a file?
you can.
Oh, you can.
So, and this is another example, is if you have problems like I have right now, instead of saying show it, well, you could do save figure. And what it does is save a PNG file, which is this same thing. And this is actually how to create these files with the save PNG. Okay? And there is an example for it. You can try to decorate your original chart a little bit, to add just a title, to add some kind of legend. So it starts getting more and more complicated. But it's just, you just need to remember, you create the legend with this. First of all, you have to extract. The way it works is just extracting the subplots, PLT1 and PLT2, and then assigning these subplots to different names for the series. Again, if you want to try, it should display as a chart.
It's nicer than the syntax is nicer required. I have to give everything I want.
That is correct, and I think the quality is better. But then, I'm talking about Matplotlib, so I shouldn't say that. But then you go to LaTeX, and then you use the TIKZ package, and the result is even better than this. So at some point, you start even using this. You stop using this because that one is so much better. But the syntax is also more complicated in LaTeX, right? But when you can do all this in LaTeX, you say, what was I doing before? So next example is just, now we are plotting NumPy arrays. Before we were just creating our own lists. Here we're just creating an array with a range. And we are just plotting this array in 3 different ways because when the plot function becomes a little bit more difficult, you create the T array with the original value with a red line. You create square by blue square, then up to 3 with green triangles. And this is the command that I was telling you before. Instead of having PLT show, you replace PLT show by PLT.savefig, and the name that you want to use, it will create a PNG file with exactly the same plot that you have here. So if you don't have an interactive X, like I don't have X right now, you can always do this. Next thing is, if you're submitting jobs to Stampede, you can do something like this at the end of your job and create a PNG so you can easily analyze the results depending on how your results are. Right? It's quite nice. This is a very trivial example of how to use bars. And there is a reason for showing this. Now we are just using the PLT bar function here to plot this -100, 200, -25, 50 thing. And we just adding some message to the X label node and so on. And this is a very trivial example. There's nothing fancy here. But you can, and this is something that you have to remember. We are using Matplotlib, but we are still in Python. You have the whole programming environment for you. So you can do more things. For example, now we're going to change the color. Well, we're just going to use Python syntax because was Python all the time. So we are just going to iterate through all the values that we have, and for those that are negative, we are going to change the color. That is something that you have to remember. This is Matplotlib, Python using Matplotlib. Matplotlib is just a library. You still have Python there, all the power of Python. So this is just a normal Python code calling matplotlib to plot stuff. Okay. This is how you plot error boxes with distribution boxes, and this box plot, I always call it box plot, that's all. So this is useful for median values, the different distribution of statistical values. It's a very typical plot. Since I cannot show real examples, it's kind of You can create figures with actually 2 figures in the same image. So this is just one plot that will contain these 2 graphs or 2 subplots. All we're doing here, we just create the subplots. In the first plot, the 2, 1, 1 is the top one. The 2, 1, 2 is the bottom one. And we are just adding different functions to each of these plots. Okay. It can get as complicated as you want it. So here, within each of these boxes, you could be plotting functions or whatever you need to plot. Okay, this is actually useful. I never found it for me, but maybe for the people it's useful. And we're just going to finish really quick with SciPy before we go to more interesting stuff. So SciPy is just a set of mathematical algorithms and different functions built on top of NumPy. NumPy is the base for many things in the Python world, and SciPy is one of them. It's organized into subpackages that cover many different scientific computation areas. And they say that it can compete with things like MATLAB, IDL, TAF, RLab, Scilab. I don't know. I wouldn't say so much, but for kind of easy things, not very big things, it works pretty well. So it has many different functions, organizing, for example, special functions, which is put whatever you have in there, integration functions, optimization, for example, optimization. The algorithms that it implements, there's nothing they can do when compared to Simplex or Gurobi, but still for smaller MILP problems, it works pretty well. It has Fourier transforms, linear algebra. Before we saw that NumPy has linear algebra, SciPy has its own linear algebra functions. Try to choose whatever works best for you. It also has file input and output and image processing. Well, I'm not showing the image processing example, but you can do image processing within Python. So part of the input-output is that you can create and load MATLAB files. The same thing goes for IDL, for WAP sound files, or even for netcdf files. Okay, this code here that you guys have in the examples, is called SciPy. This code is going to create a netcdf file with different data, with dimensions and variables, and it's going to also read it. And you don't have to worry about the netcdf module or anything like that. So even if we try here, this created this simple.nc file, which is a netcdf file. With this information, it's just created. It's kind of random information. It's just string saying that this is just created for a test. Variable. It's also saving an array in the netcdf file, and it's just loading the last element of that array that is contained in the netcdf file. Okay. So if you have netcdf files, you can export them from Python and use them in Python, like you would do with C or Fortran. Yeah, I'm going to go really fast. So this is just the stats module of SciPy. It allows you to extract a lot of information from NumPy arrays, like the mean value, standard distribution, standard deviation, sorry, the average. So many functions are just pure statistic functions. And in this case, if you run it, it will show at the end just a plot with a Gaussian, so showing that you can have SciPy plus matplotlib plus NumPy all in the same script. Okay. And the last example is just a Bessel function. So we are just solving that equation there. They always show this one to show the capabilities of 3D plotting in matplotlib. I don't understand it. If someone understands this function, we can create another tutorial. But this is the code solving that and just plotting the previous image that you just saw. So if you run this Bessel function, just Python Bessel.py, it will show you a 3D plot of that previous function. Interactive, you can move it, you can do whatever you want to do with it. Well, not whatever, this is not a very complex package, but you can interact with this graph, with this plot, okay? And that's the end of the NumPy and matplotlib as SciPy. So we just have MPI for Pi remaining. So questions before we go into this? Yeah.
So will the link stuff, the offloading, will that also speed up the SciPy? Do like a choice?
Anything that specifically makes from a library call, it could, but that depends on the specific implementation that they have.
Or and even how we compile the SciPy. I couldn't tell you because the SciPy functions are different from the NumPy function.
A lot of the SciPy functions are inherently using component.
We should, yeah.
If you have a situation where it makes sense to use component, you should probably. But you can turn the offload report on
And check.
and see, or you can go to the website, find out which specific things should be looked up, and then you have to go look at the SciPy documentation, see if they're using that offload.
Yeah. It's kind of,
It's complicated.
yeah, there's no clear answer for that. So, well, try. So, more questions? Okay. Let me do this thing. Just see. Okay, so I have it ready there. So, do you guys know MPI or use MPI? Yeah. Okay, so hopefully, I'm just saying, I don't want to go through explaining what every single MPI function does. We had MPI tutorials for that. But, okay. What's the goal of this? You can do MPI from Python. Yeah. Should you do this? Yeah, why not? I'm a really big fan of this specific model. I've been using it for a while. It's, once you know it, it's easy. Let's see. So what is MPI? You know MPI, but it stands for Message Passing Interface. It's used for in distributed memory machines. And it has many implementations with interfaces in C, C++, and Fortran. Why would you use Python with this? Well, again, because you already have your Python code and because you like Python. And they would say, well, in this case, it's true that you shouldn't be using MPI for Pi for very large simulations. So if you want to have 4,000 cores, move to C. Okay, if you're running 500, it's okay. 200, great. So it's small to medium codes. Can I use it for production? Yes, if the communication is not very free. So if you have a code that is really, really heavy in computation and just communication happens few times, Python is great for that. Okay. MPI for Pi. So with MPI, we know that each MPI program starts running as an independent process or task, and each task is going to have its own memory address space, having different processors of the machine, or nodes. There are basically two types of message passing: the point-to-point, where you have two processors talking to each other, or collectives, where all the processors will have to do something at the same time. Some information exchange. So why MPI? MPI, well, because it's everywhere in all the clusters. So that's why you want to do it. You want to use it. It matches the hardware that the clusters have. The scalability is pretty good, up to a certain number, and it avoids some complexity with memory. But just focusing on MPI for Pi. MPI for Pi is just an MPI implementation for Python. There are other implementations. Most of the other implementations are kind of old, or they are not maintained. And this one is maintained. You can see commits in the source code every single day. So there are people actually, one guy, working on this all the time. So if you talk to him, if you find a bug, he's going to fix it quickly. So it provides a very similar interface to MPI C++. If you don't like the MPI C++ interface, I'm sorry, I don't like it. The C is much better. But that's what they decided in the past, and that's what they keep using. They always say, if you know MPI, you know MPI for Pi, and it's very easy. That's not true. MPI for Pi is the most difficult MPI implementation that I've seen. Okay, it's really awful. When you don't know, it's awful. When you know what you're doing, it's great because you're using Python and you like Python. But starting with it, not easy. Then you try to go to the documentation. There is little documentation, almost non-existent. You try to go online to find examples. There are no examples. It's like, hey, I'm using the worst package ever. So you actually go, and if you really have complex requirements, you go to the test files of the module where they actually check the functionality, and they check all the functions of MPI for Pi, and you try to get examples from the ideas. It's not easy, and one of my main ideas with this part of the tutorial is to give you actual examples that cover most of the typical scenarios when using MPI. So you don't have to go to navigate around the tests because it's not easy. Okay. One good thing, one bad thing at the same time is that you can communicate Python objects. So that box that we have been talking about, which is an integer, for example, plus something else, you can communicate the whole thing without worrying about it. You just say, send this, and you don't have to worry about anything. You just send it. Internally, MPI for Pi is serializing that object and then deserializing that object and the remote now. What you lose in performance, that's what they always say with Python, you gain that in shorter development time. I don't agree with that in the MPI for Pi part, at least at the beginning, but after a while you get used to the complexity of the module. There are many MPI functions. I don't know all of them. You don't need to know all of them. And when you get an MPI book, they say, well, send, receive, you're almost good to go. And it's kind of true, okay? You can do more difficult stuff, but basically with send and receive, you could potentially do most of the stuff. One important thing is of MPI for Pi, and a difference with C or C++, Fortran, is that you don't have to call MPI init or MPI finalize. MPI init is automatically called when you import the module, and MPI finalize is called when you actually exit Python. That being said, if you really need to call MPI init in a really specific place for some reason, there is one test case somewhere in the repositories where you can check how to do it. It's not in the documentation anywhere. To run your MPI code, you guys know that here in Stampede we always use IV run. And you would think that, well, after every run, you always have your executable. When you're running Python, you call Python and your script. The problem is that Python that you're calling in our installation, because of mBappage, it has a bug, and there's nothing we can do about it. So when you're running MPI, Python MPI code on Stampede, you actually have to run IB-run and this launcher, this Python interpreter, which is Python-MPI. This Python MPI is located in this very user-friendly path. Okay, so all you have to do to use it, you can modify the IB-run and you can put IB-run /OPT/APPS/blah, Python MPI, and then your script. It's up to you. You can also export the path, like I'm going to do now. Export path equals all path. Okay. And now we have access to Python MPI. If you don't use this Python API, if you just call Python, you will see problems, or you will see a warning with cache being allocated. Funny. You will probably run into problems if you are using one-sided communications, meaning that the results will be completely wrong because of memory corruption. So just use Python-MPI for running your MPI code. Okay, it solves all the issues that we have. Remember, when you're running with Python, you can only use up to 64 cores. With Python MPI, you can use more than that, and that is a problem that we have with mBappage. We can talk to mBappage people. Even if you go to the MPI for Py forum, they talk about it, and it's just there's nothing no one can do. Okay, so now one important part of MPI are the communicators. There are three main communicators: the con world, which are all the processes involved in the communication; self, which is the process calling this self; and com null, which is it's not a communicator, but it's used for certain functions. If you're wondering, do I need it? If you are wondering that, maybe you don't need it. Usually, you just use it like assigning that com to equals mpi.com world, and you can extract some information from that communicator. You can get the rank of each process and the total size of the communicator. Okay. So this is the very first typical hello world example that you guys can run. So if we go to examples for MPI, you have to run it in the compute node. Don't run this in the login node because it's going to fail, basically. So all we need to do for this is just IB-run Python MPI hello. Yeah. And now it's doing this, it's just printing in three different ways hello and rank, whatever my rank is, from a total of size. So we are just getting the rank, doing com.rank, get rank, or just asking the global communicator like that. Okay. Initially, we just import the MPI for Py. This is how you always import it. From MPI for Py, import MPI. Okay. Have you been able to run it? Yeah. Let me say this. Yeah. So this is always a typical trigger example with MPI, completely useless, but at least just remember this is how you use it. From MPI for Py, import MPI. And here's where MPI for Py starts getting a little bit tricky. In data communication, we said before the Python objects can be communicated with the sender receive methods of the communicator. So if these methods belong to the communicator, that means that you will have to do com.send or com.receive. The send method, it uses as a first argument the data that you want to send, so the Python object that you're trying to send, the destination processor. So if I'm rank 0, I'm sending this to rank 1, for example, and a tag, which is the ID that I'm giving to this message. And the receiver will have to run data equals receive from a given source and a given tag. Okay. And this is a funny thing here when it starts. You see how send and receive are written like all in lower cases? I'll try to remember that. Okay. So this is the first sample that you can try to run. This is just a typical send and receive with only 2 processors. So you will have to actually call it like this. IB-RAM minus MP2. Otherwise, we will be running 16 cores. So we are going to run 2 MPI processes, and all they are doing is just, you can see it here. So it worked. All it's happening is that rank 0, it's sending an integer to rank 1 using the tag 11. You can see here, right? The rank 1 will receive that message. So this is going to be an integer, a Python integer. And also we'll send after that string saying, this is a message from 1. It's going to send it, it's sending this string to rank 0. Rank 0 is just receiving that with the receive here tag 22. You don't have to worry about saying that you're sending an integer, that you're sending a string or chars or anything. You're just sending the Python object, and the send and receive methods are implementing the magic to transform that into actually bytes, sending that, receiving the bytes, and serializing that, and transforming those bytes into a string or an integer Python object. Okay? And remember, this is all with lower cases. So send lowercase, receive lowercase. So this is what I was telling you before. So Python objects are transformed into byte streams. These byte streams are sent. The receiver will receive the byte stream and deserialize the byte stream into a Python object. Of course, this creates some kind of overhead because you have to serialize, deserialize. Okay. So what do we do usually in Python to avoid overheads with this kind of stuff? Well, you use NumPy again. Okay. We can send NumPy objects with MPI4Py, but we cannot send NumPy objects as Python objects. We have to send them as NumPy objects. How do you specify that? With capital S send, in capital R receive. And not only that, this receive has, before we were receiving the data as a result of the receive, now the data is an argument of the receive method. Okay? So you have send with lowercase for Python objects and send and receive with capital S or R for NumPy objects. When you receive the NumPy array, that array has to already exist, meaning that you need the memory to be allocated in the remote, in the receiver. And this is where the problems start. If you send a Python object with lowercase, meaning you're sending a Python object, you have to receive it with a lowercase receive, meaning you have to receive a Python object. If you receive it with a capital R, it's going to fail. It's going to fail saying the message was truncated or any random message. It's not going to say that you are receiving something with a method that you didn't have to use. It's just that the message is incorrect. Okay? And just talking about experience, it's very easy to get. I mean, there isn't so much difference between the function names. It's just a capital letter. So it's very easy to get confused and put the wrong function when you don't have to put it. So my recommendation is that if you're just sending numbers, just work with NumPy objects. Forget about the Python objects as much as you can. If you have a Python list, transform that Python list into a NumPy array and send the NumPy array. Avoid the lower cases as much as possible.
Can I ask a question?
Yep.
About that array has to exist, so that's a case where you would use that NumPy function to create a space, but not fill it
That's correct.
down at the receiving.
And then again, this also sometimes depends on the actual implementation of MPI for Pi. It might be that in one implementation they already allowed to do something different. So I'm just trying to give the kind of the most general approach to it. So here we're going to send. It's the same example that we had before. So one process is going to send, and the other one is going to receive. But we are just sending now NumPy arrays. So again, we will have to use IB_run with size 2, the MP2. So the sender rank 0 creates an array of size 10. We send it with, see the capital S here? We're even giving some hint saying, this is a set of integers. You don't have to do it. And the receiver is just creating an empty array and just waiting for this array to be received. Okay? This is another way to do it where you don't have to specify the MPI data type. So we are not specifying MPI.int. That is exactly the same example. Well, we are sending floats just to show that we can also send floats. So if you just run this, the first part, which is up to line 17, we are just sending 10 integers. The second part, we're sending 10 floats. And it's just, this is the receiver saying, yeah, I received this. Okay. And of course, you have to believe that it's true because, well, when I created the data in the receiver, it was empty. Okay? So it's clear that this is the data that I'm receiving from the sender. Okay. Just remember to be, if you're using lowercase, use lowercase. If you're using send with uppercase, stick to that. Yeah.
I get some kind of oscillation error. What?
Yeah, because you're running, this sample only runs with 2 processors here. You have this assert here. So you have to run IB_run minus MP2. So you're only using 2 cores for this sample. Yeah, did it work?
Yeah.
But this is, okay, so introduction, MPI introduction ends there. So books just telling you how to use MPI, they say, oh, this is kind of enough. You can do everything with this. And it's true, kind of. But there are more advanced stuff. There's more advanced stuff. For example, tag, we were saying before, I'm sending with tag 11. Well, tag can be any tag. Source can be any source. So you can be just waiting for any source to write to you. You can use non-blocking communication. The send and receive, you send a message. Well, you receive a message. When you're receiving, you don't get past the receive method until you actually receive the message. Okay? That can be quite inefficient because you might be waiting for a long time for something that still to happen in the future. So you don't want to do that in many cases. So you want to try the non-blocking communication. Non-blocking communication, people think that just non-blocking means that it's asynchronous, meaning that I just go, I type, I send, I receive, and I'm done, especially with I send. I send is just, I send finishes as soon, it just puts something in the buffer and it exits, it continues. The same way that send is no blocking per se. Send way that is put something in the buffer and it waits until the buffer has been filled to continue. It doesn't wait for the other process to receive the message. The send is not blocking that way, okay? So the same way that MPI you have I send and I receive, MPI for Pi you have I send and I receive, except that you don't have I receive in lowercase. So you cannot do I receive with Python objects. That is not true anymore in the most recent implementations, and the syntax is a little bit weird when you want to use it. But still, for what we have in Stampede and in general, think that I receive lowercase doesn't exist. That easy. You also have typical MPI test any, test all, and wait. So you create request. So you're going to create a request for a received, and then you're going to be checking that request with test or with wait. You will use the class request for that. These are two examples that you can try to run. The first one on the left is showing you how to use the status class. As I said before, you can receive from any source and you can receive with any tag. And you do it by receiving, for example, you type this in the receive method. You say the source can be any source, and the tag can be any tag. This is very useful for example, for producer-consumer models. You have a producer, and many consumers asking, well, you can just tell the producer to implement something like that, okay, and assign a different tag to every consumer. Once you receive it, you can just get the source that actually sent the message with this source equals status, get source, sorry, and the tag that created that message with get tag. So you can actually, if you were expecting tag 11 to arrive, you can check that you actually got tag 11 in that case. This one, we're also running with MP2. What it's saying is that the receiver received tag message from source 0 with tag 77, which is what the sender indicated here. Said, I'm sending destination, I'm rank 0, I'm sending to the destination 1, and I'm sending with the tag 77. Okay? And the other example that you have here is how to use request to create asynchronous communication. So this is a fully asynchronous sample. I think it's this one. Yes. In this case, the sender, is this? I'm thinking no. I can try with more than that. In this case, the sender is just creating an array from 0 to 1, and the receiver is going to 0 to 16, which is the number of cores that we have here, and the receiver is going to receive it. We create here the zeros in the receiver, and for what we are going to do is just to receive from each process that we ask for one number, and that will go to the index in that array. So from rank 0, we'll receive the number 1. I will go to the rank 1 on the array. From rank 2, I will receive number 2, and I will go to the rank 2 to the index 2 in the array. So what I'm doing is just creating requests. So I'm trying to read from every single process with the I receive, and I'm just receiving from this source. So meaning that from rank 1, I'm hoping and waiting for something from rank 2 and so on, and I don't care about the tag. And the sender, which are all the other 15 processes in our case, all they're doing is just they're sleeping a little bit just to introduce some delay there. and they're just sending one element to the rank 0. Okay? And they wait until the send has been completed. Okay? After this wait, we know for sure that the send has been completed. And also here, after this wait all, we know that all the receives have finished. So I have all the messages that I was waiting for. And this is an example of how to use asynchronous communication when you have Python objects. I told you before that you have I send in lowercase, but you don't have I receive in lowercase. So what happens if you have to use those methods and you want asynchronous communication? Okay, which is something that might happen. In that case, you will have to use an MPI kind of trick, and it's to play with the iProof function. The iProof function is going to be checking if there is a message coming from that target and with that tag. And it will return true when that is actually true. So when I'm receiving a message from target 0 with tag, in my case, whatever tag I'm using, 11, yeah, here. When those conditions are met, iProof is going to say, yeah, true, I exit, and you can actually receive it. I'm not receiving, iProof is not receiving the message, it's just telling you that there is something there waiting for it to be received. So once the iProof is true, I just actually receive the message with the receive method. And this is how you can implement asynchronous communication without having iReceive, just by playing with iProof. Okay? Just tiny MPI trick. We also include in this sample how to use the time to time your application with MPI time, W time. You get the start time, you get the end time. At the end, we will show how long it takes. So we do MPI, every-run minus MP2, Python MPI, sync. So here at the beginning, we have rank 1 was waiting for a message that had to be sent from rank 0. And this is happening because we have sleep here. Okay, we are just think that instead of having the sleep, the rank 0 is actually doing something useful, not just waiting. So the rank 1 is just going into this loop, into the while iProof loop. It could be doing some useful computation. And as soon as it receives, it says, oh, there is something here. I exit this loop and I receive the message. I receive the message 123, which is the message that the sender was sending here. Okay? And we know that this example took 2.5 seconds to run. Another thing you can do with MPI is just MPI reductions. In this case, it's just what is simulated to be doing is just it creates an array size 16, for example, let's say, and it's assigning a portion of the array to each processor. Each processor will get the individual elements of each portion of the array, sum all those elements in that sub portion, and send the result back to the main master process. And the main master process will collect the final result. If we call it, just call it reduction. This is a typical reduction, MPI reduction function. Yep. In this case, I was expecting to receive this number 499500, and I'm actually receiving it, so everything's correct. So what this is doing is just creating this array of 1,000 elements. And just if you create an array of 1,000 elements, and the position 1 has value 1, the position 2 has value 2, and so on. If you sum all the values in that array, the result has to be 499500. But this calculation has been done by by the individual elements, the individual processes, and they only took one portion of the array. With MPI for Pi, and this is where also advanced stuff for MPI, you can do remote memory access or one-sided communications. If you don't know about that part of this part of MPI, well, it's not that popular, and it was kind of quite bad in the past. It's becoming good. The performance is good now, or at least better. So all is happening here is just instead of passing messages, it's like remote memory access opens a window in the memory of each process and says this window is available for all the other processes to write or read from it. I'm not sending the message, I'm just kind of accessing the variable, okay? And this is what we're doing here. We're just creating the windows. So what we are going to do is just that all the elements, all the processes are going to write into rank 0 memory. So here we see how, if not rank 0, they are going to, I think it was that, yeah. Yeah. So I'm just going to create my, I'm going to create a vector size 10. Let's see how I put this. So rank 0 has an empty vector, and I'm creating, in each process, is creating a vector of size 10, initialized from 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 9. Each vector is going to put each process is going to put each vector, the vector that they have, in the master process, and they're going to accumulate that value to whatever the master has. So if you have only two processes, one will be writing to 2, and you will have at the end 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If you have 3 processes, meaning 2 slaves and the master, the final result will be 0, 2, 4, 6, 8 to 18, right? And that's what we are going to do here. And so we have 16. Yeah. And so that is just each process writing to the master. So they are all, you can see here, they are just all, they create their own data here, initialized, and they're just using this window, writing that data into 0, using this operation. It's just sum, okay? If you don't understand the syntax, don't worry. It's not that popular anyway. I was just showing that this is possible to do, this part of MPI. Finally, the collectives. I was saying before, what we have been doing so far is just point-to-point communication, so one process talking to another. You also have in MPI collectives, so all the processes are involved in the communication. That means that all the processes that are in one communicator have to reach the same instruction no matter what. If you're doing my communicator broadcast, all the processes in the communicator will have to reach that broadcast no matter what. Otherwise, it will fail. Okay? The same for scatter, gather, or reduction. So you can do a broadcast of NumPy objects. In this case, again, we use bcast with capital B. We are just creating an array of 10 elements, a NumPy array. The rank 0 is sending that array to rank 1. As we can see here, rank 1 is creating an empty array, and rank 0 is saying, it's going to say, well, this communication, so 0 and 1 get to this point, and now root, which is 0, is sending its own data to the other process, right? So the process 1 needs to receive, at the end, needs to have 0, 1, 2, 3, 4, 5, 6, 7, and 9. Yep. So they both have the same data at the end. Process 0 has 0 to 9, process 1, 0 to 9. this data was only created by process 0. And this is using NumPy objects. Since you can also, I've been talking about sending Python objects. Python objects are integers, but Python object can be a dictionary. You can send that dictionary here, key 1 complex, key 2 strings. You can send the whole thing same time to another processor. Okay?
You didn't have to specify the memory of the processor.
No, because these are Python objects. These are not NumPy
And
objects.
so when it goes to the other processor, it knows to grab something.
Yeah,
So it's inefficient about it.
yeah. And that's why it introduces the overhead and so on. It's nice to have the possibility to do this. Now, are you going to use it? Well, that's why if you use the receive with capital letter, I don't have memory, and the error is going to be weird.
Okay, so this is the lowercase.
Yeah.
Lowercase b. in
Yeah.
broadcast.
For the Python object. So we can call it the same way because dictionary. So you can see, so the rank 0 has already this at the beginning, and the rank 1 is receiving this dictionary, and you didn't have to do anything. Okay, you didn't have to worry about saying that you are sending this size of integer or bytes or whatever. So Python is doing everything for you, okay? Which is nice if you have to send this kind of complex object.
So what's your complaint about the guide interface? So that it simplifies all other things.
What do you mean?
Well, you started out by
yeah.
saying-
My main complaint about this is when you start mixing, you have to remember the send and receive with NumPy and non-NumPy, so capital and non-capital letters. If you try to do this if you try to do this sample with big Bcast, you fail. You have to allocate memory in one, you don't have to allocate memory in the other. If you send with capital letter, you have to receive with capital letter. Let's say that my main complaint is that the syntax is not different enough. If it was called send NumPy object, I would be happier. That's my main complaint.
I guess you could alias every single one.
You can, but still, MPI for Py is that. Okay. These are also two examples of how to use scatter and the gather functions, in this case, also for Python objects. If you want to give it a try, we're almost done, don't worry. We're just going to leave that out. Those are more difficult to see. And also MPI for Py has the ability to create different communicators. And this is important, especially if you're using collectives and if you want to say some memory. As I said, if you're using collectives, if you're using Bcast, for example, all the processes in the communicator have to reach the Bcast. What if you actually had two completely different type of tasks going on at the same time in different processes? Well, you want to have two different communicators because maybe not all of them need to reach the Bcast. And this is the typical example of how do you create a different communicator in C or C++, Fortran. It's always, this is the whole part is there. You're just taking the original communicator and splitting that communicator based on two variables that you're passing, two arguments, which are the color of the key. We are just, if the original rank of the process was even, we are just assigning one color, so all the even ranks go to one communicator and all the odd ranks go to the other communicator. So now we have two communicators and the global communicator. You can run Bcast in the sub communicators. You can run Bcast at the level of the global communicator. Save some memory. Can save some complexity in some cases. It can be useful. Again, this is more advanced MPI. If you don't need it, if you didn't know about it, maybe you don't need it. Again, you're happy. Good for you. But it's good to have it here. This is how you do it. And that's all. And that's also all for today. Yeah. If you have questions, in general about the course or about NPI, we're happy to help. If not, thank you very much for coming. We'll have more tutorials and more stuff. Also, my email is on all the slides, so if you want to send me questions on my email, whatever, I'll try to reply. Give me some time if there are many. But yeah, that's all. Okay. Thank you very much. I'll give you the infinite loop.
You're not gonna break it.
But you broke my machine.
I didn't break the machine.
The interface for one-sided calls declaring the windows as a time player.
Legation of NPI, Python,
Yeah, right. Windows.